Hello all, welcome to the class. We are moving on to module 2, which is properties of integers. Let us understand what is mathematical induction. The method of mathematical induction is based on principles called induction principle. This principle can be proved by using another principle called well ordering principle. These two principles highlight some important properties that it is called as properties of integers. Throughout our discussions, we make use of z plus to denote set of all positive integers. Set of all positive integers are the values from 1, 2, 3, etc. So what is meant by well ordering principle? The statement says that every non-empty subset of z plus, non-empty means there should be at least one element in that, and that set is a subset of z plus, contains a smallest element. It should have minimum elements, starting element in that set. An alternative way of stating the same principle is that set of all positive integers is well ordered always. The induction principle is as follows. Let S of n denote an open statement that involves positive integer n. Suppose that the following condition holds. The first condition says that S of 1 is true. The second statement says that if whenever S of k is true for some particular but arbitrarily chosen any integer from the set z plus, then S of k plus 1, the next element, is also true. Then S of n is true for all the values of z plus. Excuse me. Method of mathematical induction, which has two steps, basis step and induction step. A basis step is written as verify the statement S of 1 is true, that is verify S of n is true for n equal to 1. And induction step says that you have to assume that statement is true for n is equal to k, where k is a positive integer. Show that S of k plus 1 is also true. That is called induction step. Okay, we are moving on to first problem. Prove mathematical induction by mathematical induction all positive integers n greater than or equal to 1, the following statements. So as per the explanation of the definition, we have to denote S of n as this, and as per the basis step, what you should do is put n is equal to 1 starting value as per the given condition and check is that S1 is true. What is going to happen for S1 now? When you put n equal to 1, left hand side you will get only one term, and in the right hand side you substitute n equal to 1. So it is equal to 1 by 2 into 1 plus 1. It becomes 1 is equal to 2 by 2. 1 is equal to 1. Next induction step says that assume that S of k is true. So after assuming that, we have to prove it for Sk plus 1. So for that, Sk plus 1, what we have to prove is Sk plus 1, and we will see that what we have to prove in the given statement. When I substitute k equal to 1, it becomes k plus 1 is equal to 1 by 2 into k plus 1 into k plus 2. This we have to prove. So for that, what we do is I will take the left hand side of my proof to be continued, and I will try to prove that is equal to RHS. So LHS can be, consider the LHS, start simplifying it. 1 plus 2 etc. Kth term is also there before k plus 1th term. I will show here. Now for this we can apply our assumption step. From the assumption step, previous step, this value is going to become half into k plus 1 plus k plus 1. Now we simplify this just by taking LCM and all. So it becomes k plus 1 is a constant outside, it's there here and here. I will take it out. K by 2 is left over plus 1. If I simplify this, it becomes k plus 1 into k plus 2 by 2. This is same as the right hand side which we supposed to get. That is how we are going to solve this. Conclude that S of k plus 1, S of n is true for all the values greater than or equal to 1. That is what final proof.